this is not the easiest.
Yeah, real talk, this is probably behind the vectors chapter, the second hardest thing we do in second semester.
So from here on out, it's going to change.
But the good news is, I think from here on out, the things that we're for sure covering are mostly review or small extensions of ideas we saw in Algebra 3-4. So if you dug Algebra 3-4, things should lighten up here considerably, which is good, right? Well, end of the year has mostly some of the easy stuff in there rather than cramming some of the hard stuff through at the end of the year. You know, so that's good. But yeah, real talk today. This can be a challenging chapter because it's, again, all these ideas are pretty much brand new. Okay. So if you have an A game, you definitely want to bring that here. Particularly today, I think can be kind of a tough day. So we'll do the best we can with it, okay? So in chapter 10, we're going to be talking about parametric and polar functions. And we're basically going to split this kind of right down the middle. The first two sections are going to be parametric things, and the last 2 or 3 sections will be like polar things. But where I really want to start here is kind of a little bit of a motivation for why, right? Because that's, we've had this, what we've been currently describing, what we've been currently studying, we would call Cartesian functions. So up to now, what we've been talking about are called Cartesian functions, named after the Cartesian coordinate system, like the XY axis, named after the French philosopher René Descartes. He's the I think, therefore I am dude. So one of the major philosophical questions is always how do I know something is true? And his argument was the only thing that you know for sure is that you exist in this moment because you have a brain that's thinking. Everything else observed around you could be some kind of elaborate illusion or hoax perpetrated by some evil genius, which is basically the plot for the Matrix movie. Anyways, that's an interesting aside. So when we defined a function, how did we define a function? Anybody with a memory-ish of what that would be, the definition of a function? Okay, that's a reasonable shorthand. So we'd say a function is a set of ordered pairs where every member of the domain, i.e. your x's in your case, Sophia, are paired with exactly one element, or I should say member of the range, i.e. the y's in your example, Sophia. The exactly one part is the important part, though, which you had. So when we defined a function way back when, what was the easiest way we had to check if something was a function? Vertical line test, right? So things like a circle, we said were not a function. And I'm going to be a little bit specific there and say not a Cartesian function. What we'd like to do here is say, okay, well, fine, whatever, not a function. Is there a new way that I could define how my system works so that so I can make something like a circle still fit that definition of a function we had from before? So I want the whole circle, not just a part of it, but the whole circle to be able to consider it a function based on that definition that we just gave. Now, the way we've currently defined things in a Cartesian function, we're not able to do that. We have to develop like a new framework to do this. So before we were talking about just like our functions being these sets of x, y's, right? What we're going to do is instead of our ordered pairs being x, y's, what if we have some new parameter as our input and the output now is a point? Instead of before in our Cartesian system, where our input was x and our output was y, what if we have a new input being t, some parameter t, but our output is an ordered pair? If I do that, as long as the t's are only going to one point, we can have things that fail a vertical line test when we plot x, y's, but still meet the definition of a function because each t is going to its own specific point, but some of those points could have the same x values, right? So for example, if we just have this meets our definition of a function, right? The inputs are only going to one output, right? But this would fail a vertical line test if I plotted my x, y's, because 1, 1 and 1, 2 are definitely on the same vertical line. So that's essentially what we're doing with a parametric function. So we'll say our parametric function is some f of t, and we're going to define the x-coordinate for our graph in terms of t, and our y-coordinate in terms of t, and then have t defined over some kind of interval. So these guys are called parametric equations. T is called our parameter. This I is our parameter interval. freshman. That's all I have to say about that. So just a little bit of vocab here before we dive in and do some specific examples here. Most of what today is going to be is just kind of getting used to what these parametric functions are, kind of what they kind of look like or behave like, and then translating back and forth between Cartesian form and parametric form. Okay? So that's mostly what we're going to do today. Uh-oh. Okay. So we're just going to do an example here. I've given us a parametric function where f of t is defined as x of t equals t squared plus 1 and y of t is equal to 2t. And then we have 4 different situations for the interval for t, the interval for our parameter. So we're going to use our calculator to do this. Just minimize that. So if you have your calculator with you and you'd like to follow along, I encourage you to do so. If you just feel more comfortable sitting and listening, you can sit and listen. That's okay too. Whatever you're into. Okay. If I'm going to be using parametric functions, this is a decidedly different situation. So the first thing I'm going to do is I'm going to go to my mode button here next to the blue second button. And I'm going to find my 4th option where it says func, pol, and seek. And I want to change from func to par. Par being short for parametric. And if you haven't changed your calculator, if you're still in degree mode, which you probably would have been for last chapter, I'd switch back to radians since we're going to be doing graphing stuff. When we graph, we typically want to be in radians rather than degrees. So if you're in degrees still, might as well change it to radians right now while we're there. Everybody cool? So now if I go and I press my y equals, looks very different, right? Instead of saying y equals, I have an x of t and a y of t. Because every parametric function has 2 parts, I'm going to clear out the stuff that I had in there. In place of x of t, I'm going to write t squared plus 1. Notice when I press the variable button right next to the alpha, instead of giving me an x, it's automatically giving me a t because I switched to parametric mode and the independent variable in parametric mode is t. So I have t squared plus 1. And then where it says y of t, I'm going to type in 2t. God bless you. You're welcome. Does everybody feel okay doing that? Okay. Next thing I'm going to do is go to my window. So I'm going to first start by setting my X and Y window. I'm just going to set that to be -10 to +10. My suspicion is for most of us, that's probably the default that it was already at. Now, the part that I'm going to really care about here, though, is setting my interval for my parameter, setting my T-min and my T-max. So if I'm setting, if T is defined for all real numbers, really T-min should be negative infinity and T-max should be positive infinity, right? Now, parametric mode can be sometimes picky about if you're given it something that it too big or too small, like you can overflow your calculator or whatever, and then it throws a fit about it. I usually just pick something that's going to be like big enough to fill the screen that I got. So like -10 to +10 is plenty big to fill, for T to fill -10 to +10 on the X and Y. Since we're taking the T's and either multiplying by 2 or squaring it, you'll get plenty big enough to cover what we have there. So if I hit graph now, there's my parametric function. Looks like this sideways parabola. Note that in the Cartesian form, we could not have graphed something like this, right? This would not have counted as a function. Our calculator could not have handled this with a single equation. In parametric mode, though, no problem. Everybody feel okay? Yes? I just use whatever the default was. So whatever your calculator was set at, the t-step doesn't really matter. Just needs to be like appropriately small enough. So like 1 would be a problem, but if it's 0.1 whatever, like whatever. Is that okay? The t-step is basically like, it's going to go like, like I start at -10 and the next thing I'm going to do is, -0.987, yada, yada, like it's telling me the next point to do. So you want it small enough that you get a good curve out of it, but not so small that it takes like an hour to graph the thing, because you're doing like, your t-step is like 0.00001 or something, and it's like so many points the calculator has to generate. So, but it doesn't really matter much. Is that okay? Okay. So there's our picture. Let's now do part B. We're going to change the T-min to be -3 and the T-max to be +1. And then just hit graph again. Notice what we got now is just a part of that sideways parabola, right? Note again that this is still something we'd be incapable of graphing in Cartesian form. This fails a vertical line test. And in addition, notice that this has a decided stop and start. In the Cartesian form, was it easy to generate something that like just a segment like that? No way, Jose, right? That was a pain in the tuchus to try to get something to do that. If you even figured out how to do it at all, which I'm not even positive you can do it easily on this calculator. So, but getting a segment, just a part of a graph in parametric form, no problem. We just mess with the t. Let's change that now from -3,1 to -1,2 and see what we get. So we got a little bit different piece. Notice it's just a part of it. It's a finite part of it. It has a decided stop and end, but just a part. And then our last interval was -2 to 3. So again, we'll go back and change our T-min and T-max. And again, in a different piece of parabola. What do you guys think? So the interval for t matters a lot, right? You get a decidedly different picture depending on what that interval is. The domains and ranges for these functions that we just graphed would be decidedly different depending on what the t is, right? So that part matters a lot. just to illustrate. Let's look at another one. So we'll look at a different graph here. I guess I'll call this So let's say we have this parametric function. What's this graph going to be? No? You know what this is. In fact, you've seen this graph before. Many times. This is the unit circle, right? Remember the unit circles, every point on the unit circle, the coordinate was cosine theta comma sine theta. The x-coordinate was cosine and the y-coordinate was sine. And it was defined for one full rotation from 0 to 2 pi. So that is exactly what we're going to get here. So if I do cosine t, oops, that's not what I wanted to do there. Press the wrong button. Cosine t to sine t. And I'll change my window from 0 to 2 pi. Notice when I do put in 2 pi and press enter on my calculator, it automatically converts that into a decimal. And just so that my picture is not like itty bitty teeny weeny, I'm going to probably just change that from like -3 to +3 in the x and y direction. So when I graph my unit circle, it's just not like a little itty bitty teeny thing. Although it's fine if you just hit graph and it's a teeny little circle. Is everybody okay with that? And here's another situation where, like, if your t-step was absurdly small, this might take a minute for your calculator to get this thing to show up. If it's taking too long, make your t-step a little bigger. I think this might actually, the t-step I have now might be actually like pi over 24. Yeah, that's what that was. It looked like a fraction of pi when I saw it, because it was like, why would I get that kooky of a decimal? Where did that kooky decimal come from otherwise? It was a 24th of pi. Why a 24th? I don't know. Probably because it's divisible by all the unit circle angles. Can divide 24. Fourths, sixths, and thirds. Anyways. Everybody okay with that idea? So again, we're just talking about kind of like building some intuition up as to what these things look like, these parametric curves. So what we want to talk about now is going back and forth from parametric functions to Cartesian functions and going the other way as well. So when we talk about going from a parametric function to a Cartesian function, the direction is typically something like eliminate the parameter. And to go from Cartesian to parametric, we usually say parameterize the function or something like that. So we're going to start by looking at this direction, going from parametric to Cartesian, as this one is typically the more difficult of the two. So my first example here, oh well, I tried. F of t is equal to x of t is 2 minus 3t, and y of t is 1 minus t. So to eliminate the parameter, what I'm going to do is I'm going to start with the independent variable. But instead of writing x of t, I'm just going to write x. And then all I'm going to do with this is just get the t by itself. So I'll subtract 2 from both sides. And then divide by 3. Or I should say negative 3. Everybody's cool there? Then I'll take the independent variable. But instead of writing y of t, I'm just going to write y. And then I'm going to plug that value for t back in that I just found a moment ago. And just simplify. Is everybody okay with what I've done there? So I just take the parametric equation for x, get the t by itself, and then I plug that into the parametric equation for y, thus eliminating the t's. But there's a catch. What's the catch? The domain and range is the catch. If I were to look at y equals 1/3 x plus 1/3 as a Cartesian function all on its own that didn't come from a parametric, what would the domain and range for that be? I should be able to do this at this level without a whole lot of thought. The domain and range of y equals 1/3 x plus 1/3, assuming I'm just asking you that question, not that it came from a parametric. No. It would be all real numbers for both, right? What type of function is this? It's a linear function, right? So we have one end points up and one end points down, going in both directions forever, correct? But we've seen that parametric functions could just represent like a segment of that, some portion of that, in which case the domain and range here would not be all real numbers each. We have to think about this a little bit more carefully, right? So we do need to indicate the domain and range to go along with this because it's not guaranteed. To just be all real numbers. So let's talk about how we can ascertain that. So the x-coordinates is what we're talking about when we talk about the domain, right? Everybody agree with that? So the x-coordinates for our Cartesian function are generated by the parametric equation for x everybody's okay with that. In fact, let me be a little bit more specific. Are the outputs of, instead of generated by, let's be specific, a little bit more specific. That's probably a better word to use there. What are the inputs to that function? The interval for the parameter, correct? So what that's saying then is that the range of x of t gives the domain for our Cartesian function. Okay, if all the x coordinates for our Cartesian are coming from the parametric equation x of t, in fact, they're the outputs of that equation x of t, and we have a set for the inputs, that's the parametric interval. So in this case, what type of function is x of t? This should be a trivial question for students at this level. Does it look like mx plus b? Yes, so it's a linear function. Okay. We're told the domain of the linear function is all real numbers. So what does the range have to be? Also all real numbers, because it's going on forever in both directions. To the right and left, it has to be going on forever up and down. Everybody agree? Okay. So in our case, the range of x of t is all real numbers, which tells us then the domain of our Cartesian is also all real numbers. Is everybody okay? If I need to slow down or re-explain anything, holler at me. What you're doing now is not trivial. This is a difficult concept, right? As you're translating back and forth between these two function types and translating domains and ranges between the two function types, which is not trivial. That's not an easy thing to do. Okay, so if you need me to slow down or you need to hear it again or you just need a minute to think about it, holler at me. Okay, I'm trying to go slow through this and provide a lot of like stoppages so you can process a little bit. All right. So to do the range for our Cartesian, it's the same idea. The y coordinates make up the range. And those are the outputs of the parametric equation for y, which also has inputs of all real numbers. that tells us then the range of that parametric equation for y gives the range for our Cartesian function. Yeah, Grace. Of course. So let's look at this situation. What type of function is the parametric equation for y? Linear. And since the domain for that linear function is all real numbers, what can we say about the range for it? Also all real numbers. Oops. So I can write that in up here also. Oops. Okay. So what part of our parametric function is definitely going to affect our values for the domain and range? Is this interval for the parameter? So let's just say hypothetically, instead of being all real numbers, let's assume that the interval for our parameter goes from -4 inclusive to 2 exclusive. So that interval is closed at -4 and open at 2. So we're just going to kind of go back and off to the side do the same thing here, except assuming that we have this different interval. So if I think about this, this is like a t, x of t axis. I'm going to have some kind of segment that looks like that. Is everybody okay with that? Where this end is -4, x of -4, and this end is 2 x of 2. The t over here. So we're looking at the graph of x of t is equal to 2 minus 3t to kind of justify how we're about to find the range of this. So the range is going to go from x of 2 up to x of -2, or x of -4. Yeah.
Sorry,
Check.
what is this graph again?
Yeah. This is the graph of x of t equals 2 minus 3t.
Oh. Oh.
So we're just going back and redoing the problem as if the parameter interval was now finitely long instead of being infinitely long. Is everybody okay with that? So when we do this, that range of x of t is going to go from -4 to 14. If I look at my picture, I know at -4, that is an open interval, because this is really my -4 there. This is my 14 up here. So I'm going to use a parenthesis there. But the 14 is up at the closed interval, so I'm going to use the bracket there. Can somebody grab the door for me? Thank you, Priscilla. Which would mean then the domain for my Cartesian function is the same. Is that okay? Again, this is not easy, right? This is very different than kind of what we've been used to. Domains and ranges are already kind of a difficult concept. And now we're talking about translating back and forth, kind of stepping through some different pieces and making sure you're talking about the right domains and ranges, right? That some part, I have to consider the domain and range of that part to figure out the domain and range of something else, which is a little bit of a layer to kind of walk through. Let's do the next one. The one for the, let's do the range for the Cartesian. So we're going to be doing the same thing. So again, we have y minus 4x. What did I say? What? Y of t equals 1 minus t. I don't even know what I was talking about. Words came out and they were not even the words that I wanted. So again, we have a linear function with a negative slope. So again, this is a t, y of t axis, where we're graphing the function. Y of t equals 1 minus t. So again, the range for this function is going to go from y of 2 to y of -4. Going to go from the minimum to the maximum. Y of -4 is 5. And y of 2 is -1. So my range for my parametric curve goes from -1 to 5. Notice that the point where -1 is the y-coordinate, that point is open, so I'm going to use a parenthesis. And at the point where 5 is the y-coordinate is a closed circle, so I use the bracket. So the range for our Cartesian function is the same then. Doing okay? Okay. Again, trying to go slow and take some breaks after we do some things to let this not feel like it's a copying race and you have a little bit of time to process and think about it as we're going. You guys ready to do the next example? Okay. Okay, good. I did label that as an A. Yes.
That x is equal to negative 4t.
Oh, I should say, yeah. That's Mr. Gulick's making typos here. Yeah, thank you. X of t is equal to negative 4t. Y of t is equal to 2t squared plus 1. Guys, do we need to revisit that previous example before I move forward? You're okay? Okay. If you do, say something. We can go back and talk about it for another minute. Makes no sense to start the next one before we've got feel like we got the previous one under control. No problem to go back or to repeat or whatever. This, again, I know this isn't easy. We're trying to go slow and be careful, right? Notice the pace here slowed down tremendously compared to some of the previous things we've done, right? This is me acknowledging that I know this is difficult, and we're trying to build in some time to process while we're doing things. Okay, so we'll start just by eliminating the parameter. That's typically going to be the easy part. So I just rewrite it as x equals and solve for t. Then I write it as y equals and plug in my value of t back in. Guess I'll write it that way. Probably makes more sense. 1/4 squared is 1 over 16, and times 2 is 2 over 16, or 1/8. So there's eliminating my parameters. So I'll have a domain, and then I'll have my range. We'll fill those in here in a few moments as we kind of work through that process. Yes, Amanda. Oh, sure. So that's a negative there, but the squared still blows up the negative sign. So yes, I did forget to write the negative in with it, but thankfully here I didn't get punished for that because the squared gets rid of the negative. But yeah, absolutely, I forgot the negative sign there. Thankfully, it was a one editor mistake instead of like, oh yeah, I got like 5 things to edit now mistake. Okay. So let's do the domain first. which parametric equation do I need to look at for the domain? X of t, right? So I know the outputs for x of t are going to give me my domain for my Cartesian function. I know the inputs are -2 to 4. Notice that the -2 is inclusive and the 4 was exclusive. So what type of function is x of t here? Linear, right? So I'm just going to have, something that looks like this, right? Everybody agree with that? So the only things we care about are the endpoints, because that's giving us the maximum and minimum for our function. I'm just going to make a little star next to the x of 4 to remind myself that that's coming from the open interval. So I get 8 here. I get -16 there. So we're going from -16 to 8. And the -16, again, we're using the parenthesis because it comes from the 4 that had the parenthesis in the domain. Are we okay with that? So that's not so bad, right? Now that we've kind of run through it once and we've kind of built out the foundation, it's like, oh, I just plug the 2 endpoints in and I write a, small to big, and the worst I have to really worry about is making sure that I got the bracket and parenthesis parts squared away. But that's not so bad. The range is coming from which parametric equation? Y of t, which is 2t squared plus 1. What kind of function is y of t? What kind of function is y of t?
Parabola.
Okay, the graph looks like a parabola. The name for that, though, is quadratic.
Yeah, quadratic.
Okay, so when we have our parabola, we could have something that looks like this. Or, you could have something that just looks like that, right? So we have to make sure, because if it's this one on the right, all we need are the endpoints. But if it's the one on the left, what other point do we need? That's the vertex, right? That's what we call that point. Actually, I drew this the wrong way, didn't I? This should be a parabola opening up. But whatever, you guys will forgive me. No, you won't. I'm going to fix it. You guys are jerks, I know it. There. So this is -2, y of -2. This is, I'll say, xv and yv, v for vertex. And this is 4, y of 4. So this is the scenario there that we really have to worry about, right? It'll be really easy once we find the vertex to tell if we're in that scenario or not. Who remembers how to find the vertex for a quadratic? calculator. Sure. Well, again, this is something that we would have talked about last year that I hope that we would be able to remember. Actually, I'm going to use f of x. Actually, let's just say, grammar this up a little bit. The is negative b over 2a comma f of negative b over 2a. Does that ring a bell? No? If it didn't, make sure you write it down and put a box around it, because you will run into quadratics from time to time dealing with this. So should be able to find the vertex for a quadratic. That's an unrealistic expectation for students at this level. So if you don't remember, there's our situation. So again, here's our quadratic. So the vertex is at 0, 1. So here, notice that my vertex is inside the interval for my parameter. So we did have the first situation going on. If hypothetically that vertex was like 6, then it would be like the second situation and the vertex doesn't matter. So you guys okay with that? Dominic?
Can you say that again?
Sure. Notice that my vertex 0 is inside the interval for my parameter. 0 is in between -2 and 4. So it is like the picture on the left that I drew, where the vertex definitely matters. If hypothetically the vertex was at 6 or something that was outside of that interval for the parameter, then our situation would be like the picture on the right, and the vertex wouldn't matter. Is that okay, Dominic?
Yeah.
Okay. So here that is going to matter. And then we just have to do this. So what do we got here? That's 9. And 33. And again, I want to point out that the 4 had an open interval, so the 33 is also going to need an open interval there. So when we put this together now, we're going from 0, grab a different color here, to 33, right? So amongst those 3 outputs, 0, 9, and 33, 0 is the smallest, and 33 is the biggest. 0 gets a bracket because it's definitely included in the numbers between -2 and 4. Oh, not 0. God, confound it, Mr. Kulik. Should be a 1 there. But 1 gets a bracket because 0 is in between -2 and 4. And 33 gets a parenthesis. Yes,
When
Aiden.
we're looking to see if the vertex fits in the t values, are we looking at the 1 or were we looking at the 0 to see if it fit in?
So you're looking at the 0, the value for t, right?
Okay, yeah, that makes sense.
Yep. Yeah, these are good questions. Again, you know, it is not trivial what you're doing. This is tricky. I want to point out to you that what if this was the other way? Does that make a difference? Let's just kind of illustrate as a picture. So here we have -2, 9, and then we have 0, -1, and then we have 4, 33. Oh, I'm sorry, that shouldn't be 0, -1. That was 0, 1. Sorry. So my low point would be 1. My high point would be 33. Does it matter that this is not included? Did that matter when I wrote my interval, or when I wrote my range there? It doesn't, because somewhere over here you have something, comma, 9 on that side. So 9 is used. Even though it's not used at that one end, that's okay, because it's used on the other side, so you don't have to worry about it. I know. It's a lot. It's a lot. By and large, what do we really need to be? I'm doing a lot of like hypotheticals inside of this. Overall, though, what are we really doing when we're doing this? Just checking the endpoints, and then if there's like an extreme point that could be outside it, could be something other than the endpoints, right? So, for example, if you have a quadratic or a cubic or a quartic or something, you'd have to worry about those extreme points. But that's what it boils down to when we're checking these. Yes, certainly. You can just go right now. I think we're big boys and girls and can. I know. Well, I don't. I mean,
No parties in the bathroom, sorry.
yeah.
Because the team calls between the
Yeah.
Is everybody? We're doing okay? Okay. If you have clarifications or more to follow up with, like, go ahead, fire off a hypothetical. You can fire off like, hey, why is that again? Like, I can repeat. It's not a big deal. And again, like, we can hit this again next time with questions after you have a chance to try some of these things. So don't feel like it has to be perfect today, right? All right.
What is a quadratic? So when you see like the feet on the split.
All right. What if we have this function? F of t is equal to, oh shoot, I forgot my x of t's and my y of t's. So I don't know. Why would you try doing anything other than just starting the way that we would have started? So we'll say x equals and get the x by itself, or get the t by itself. And then we'll say y equals and plug the t in, and then, oh, Boise. What, that doesn't look, that looks bad, right? Hayden?
Why is the x just equal to cosine t?
Oh, sorry, 3. Sure.
Okay.
Forgot that. Sorry. Yeah. You're right. No, keep it on there. Like, if you see me making mistakes, you stop me as soon as you see them. That's good. Sometimes they're not mistakes, and it's just like we overlook something, but a lot of times Mr. Kulik makes some mistakes. He gets going, he gets excited, and stuff happens, you know? But look at this thing. Yeah, that looks positively horrible, right? What does that, how would you go about graphing that in a Cartesian sense? Like, oh, Boise, I don't know. Instead, let's do this. Let's take a look at the picture, because we can graph this on a calculator, and see what we're supposed to be getting. Right? Let's do that instead. Okay. Da-da-da-da. Guess I'll make that a little bigger. All right, so there's our picture. What do you guys see? What shape is this? Circle. You sure it's not an oval? It is a circle. Why does it look like an oval but still is a circle? You have a rectangular display instead of a square display, so it distorts everything. These are important things to cover, though, right? This still is a circle. How can you tell? 1, 2, 3 radius. 1, 2, 3 radius. Everybody can count? Okay. So what we're seeing is a circle with radius of 3, right? Okay, geometry all-stars, who remembers the equation for a circle? That's you're talking about are you giving me the area of a circle? No, the equation for the graph of a circle.
Oh, it's the square. I remember. I can't remember.
So there's 2 pieces that you need to graph a circle. You need its center and radius. If you don't remember that equation from geometry, you might want to write that down. That'll come up here periodically. So if I go back and I look at my picture, what other piece of information do I need for my picture in addition to the radius? The center, which appears to be 0, 0. So what do we have then? Or just x squared plus y squared is equal to 9. Everybody's okay with that? Now all we'll do is check to make sure that what we pulled from the picture is actually what's going on. Everybody's okay with that? How do I find the x's according to my parametric? Well, that's 3 cosine t. So I'll plug that in for x. How do I find my y's according to the parametric? 3 sine t. So I'll plug that in for y. And I'll check to see if that indeed equals 9. Everybody's okay with that? 3 cosine t times 3 cosine t gives me 9 cosine squared t. 3 sine t times 3 sine t gives me 9 sine squared t. Can factor out a greatest common factor of 9, and what do you guys see? I see a Pythagorean identity. What's cosine squared plus sine squared equal to? 1. So we're good. As an alternative, we can do that. Why does the domain and range not matter here? Well, because the circle is going to just be, like the t could be all real numbers and you'll end up still with the same thing because it'll just draw the circle over itself a million times here. So we're not going to worry so much about that. Okay. Oops.
Wait, so Mr. Ford,
Yes.
what would we leave for an answer for that problem?
So this is your answer.
Okay.
We just check to make sure that our picture.
We just made sure that was like correct, right?
Yes.
Okay.
Yes.
Using what?
Yes.
The x squared plus 9 squared plus 9 was the answer.
Actually, the best.
Nobody did the main range of the circle. And like the corner
I didn't mean to be done.
Okay.
Yeah, we didn't get as far as I wanted to today. That's okay. It's not a big deal. It's okay.
The question was,
So, shh. The question for all these A, B's, and C's have been to eliminate the parameter, was the direction, which basically means convert your parametric equation into a Cartesian equation. Okay? So that's what we've done in all 3 of these examples. Some of them, the domain and range mattered a lot. And that last one, the domain and range really didn't matter. You could pull it from the picture. Okay. What if we want to go the reverse direction? What if I can do this in 5 minutes? It's not. This part isn't hard. So let's say we have this equation, and I want to write this as a parametric equation, or as a parametric function. First things first, does this pass a vertical line test? Yes. So if that's the case, then to write this as a parametric function is super duper easy. What's the independent variable in our Cartesian form? X. What's the independent variable in our parametric form? T. So we're just going to set those equal to each other. Okay with that? So what does that make y have to be? Woof, how nice is that? And then the last thing I need is to give the interval for t. Since we set t equal to x, the domain from our Cartesian is going to be the same as the interval For our parameter, what's the domain for y equals 3x minus 2? All real numbers. Piece of cake, right? I have two more examples to cover. We'll pick those up next time. So at this point, you guys can do approximately 1 through 40 from the problem set. Hey, look. Everybody take a deep breath. Take a deep breath. We're going to finish up 10-1 on Wednesday. We're going to do 10-2, probably. We'll see how many questions we get. And then for your virtual days, it's just going to be work on your stuff. Okay? The problem set for Sunday is just going to be 1 through 40. Whatever else we add from 10-2 would go into next week's. So not a big deal. I think there's only 9 problems in the next section for 10-2. I think there's only like 9 problems involved, so it's not like it's a ton anyways, but push it all into next week. It's not a big deal. Everybody feel okay with that? Okay. And you guys can bounce. We're good. Have a great day.
Let me push back to my next Sunday.